Good morning, students. So, the last previous video we have discussed the conduction and mechanism of conduction. Okay. Also, we have discussed the good conductors and also the bad conductors. Okay. So, we have discussed that the mechanism of thermal conduction, that how the heat can be transferred. Okay. How it transfers? As we know that according to the kinetic theory, that it says that according to the kinetic theory that the average kinetic energy of the molecules of any system is always directly proportional to the increase in the temperature. Greater the temperature, greater will be the average kinetic energy of the molecules. Okay. Now, in today's class, we are discussing the thermal conductivity. Thermal conductivity. What is this thermal conductivity? I define it. Okay. So before that, I will explain that by taking an example. That let us consider a cube. This is a cube. This is phase 1, this is phase 2. We have considered a cube here, a cube of having the two phases. This is phase 1 and this is phase 2. Distance between these two phases is delta x, and at the two phases we have maintained a temperature. At this phase we are having the temperature is theta plus delta theta. And here we are having a theta. Okay. Temperature at the phase 1 is theta plus delta theta. Temperature at the phase 2 is theta. Okay. And here A is representing the area of phase 1. Here delta x is representing the distance between the phase 1 and phase 2. Okay. Now here, as here it is a high temperature, as it is indicating that theta plus delta theta, here phase 1 is a hot phase. It is a hot phase where the temperature is higher. Now obviously we know that the heat flows from hot body to cold body. Okay. Now the flow of heat will be in this direction. Say it is flowing from phase 1 to phase 2 in this direction. Okay. Now here, so whatever the heat it is flowing, heat energy which is flowing from phase 1 to phase 2 is directly proportional to the heat flowing from phase 1 to phase 2 is directly proportional to area of phase 1, area of phase 1, and it is directly proportional to temperature difference. Temperature difference is delta theta. It is P. Okay. It is also directly proportional to. It is also directly proportional to time, that is T. Okay. And it is inversely proportional to. It is inversely proportional to distance between phase 1 and phase 2. Okay. The amount of heat which is flowing from phase 1 to phase 2 is directly proportional to the area of the phase 1 and it is directly proportional to the temperature difference. Temperature difference. It is theta plus delta theta minus theta. We get the delta theta. Here delta theta is the temperature difference between the two phases. And it is also directly proportional to the time elapsed. Okay. Okay. Now it is also directly proportional to the time also. In how much time the heat is flowing here. And it is inversely proportional to the distance between the phase 1 and phase 2. Greater the distance and lesser will be the heat flow. Okay, so this is what the heat which is flowing from phase 1 to phase 2 is depending on all these 4 factors here. Okay, so in the equation form we are writing here, that is here Q means heat which is flowing. I am writing here, it is Q. Okay, the heat flows from phase 1 to phase 2 is, that is Q. Q is directly proportional to, okay, is directly proportional to area, change in temperature and the time, and it is inversely proportional to, that is delta x. Okay, delta x. Here I have written here delta x. Inversely proportional distance between the two phases, that is delta x. Directly proportional to area, directly proportional to the temperature difference, directly proportional to the time, and it is inversely proportional to the distance between the phase 1 and phase 2. Okay. So if I remove this proportionality constant, it is minus k 8 delta theta t divided by delta x. Okay. Now this negative sign, it is indicating that where k is the thermal conductivity. K is the thermal conductivity, and here negative sign indicates that decrease in the here actually here we are denoting this as minus delta theta by delta x. Okay, here I am writing this as minus delta theta by delta x indicates the temperature gradient. Indicates that temperature gradient. Here, with the change in the temperature, with the change in the distance, the temperature is also decreasing. Greater the distance, okay, now lesser will be the temperature. So here, that is what here negative sign is indicating that the temperature is decreasing with the distance. Temperature is decreasing with the temperature. Negative sign shows that decrease in temperature with increase in distance. Okay. So that is what the amount of heat is directly proportional to the area of the phase 1, and it is directly proportional to the change in temperature, and it is directly proportional to the time, and it is inversely proportional to the what we can say is distance between the phase 1 and phase 2. Here this minus delta theta by delta x, minus theta by delta x, it is representing the temperature gradient. So it shows that the temperature is decreasing with the increase of distance. Okay, so that is what this expression is expressed here, that always this amount, the heat flows will depend on these all four factors. Now if I rearrange this expression here, I can write this as k equal to minus of q divided by t. Okay, if I take this in the numerator, then it becomes q by t whole divided by a into delta theta by delta x. So this expression, it shows the thermal conductivity definition. I have written this k here. We have taken this minus in this side and t in the denominator of this q. So q by t whole divided by a into delta theta by delta x. Okay. So if here, if area is equal to 1 meter square, now if the delta theta is 1 degree Celsius, that is change in temperature, and if time is 1 second, and if the distance between the two phases is that is 1 meter, then if I substitute all these values here, area 1, time 1, delta theta 1 degree Celsius, delta x as 1 meter, then here k is equal to, that is minus of 2. So if I remove this negative term here, so numerically the thermal conductivity will be equal to the amount of heat which is flowing from phase 1 to phase 2. So this is the, what we can say, the how can we define this thermal conductivity here? So we can define this thermal conductivity as here the amount of heat which is flowing, okay, the amount of heat energy which is flowing from the phase 1, which is at a distance of 1 meter, okay, which is the distance at 1 meter, and the temperature difference between the phase 1 and phase 2 is, that is 1 degree Celsius, will be always equal to the, that is thermal, what we can say, this amount of heat, that is thermal conductivity is equal to the what, that is amount of heat. I will write the exact definition here on the board so that you can note down the definition of the thermal conductivity. So this is what I have written the definition here. The thermal conductivity of a material is defined as the quantity of heat energy that flows across the opposite phases of 1 meter cube in 1 second, and the opposite phases of the cube is maintain the temperature difference of 1 degree Celsius or 1 Kelvin. So this is all about the thermal conductivity of the temperature, and you should remember that here this thermal conductivity depends on the nature of the material. Remember this. Thermal conductivity depends on the nature of the material. Now let us discuss the units of thermal conductivity. In CGS system, the unit of thermal conductivity is calorie per second, okay, per meter and per Kelvin. Okay. Now similarly, in SI system, it is joule per second, per meter. So here per degree Celsius. You see the system per degree Celsius, and then it is per Kelvin. Okay, or also you can write this as we know that joule per second is equal to what? That is we can also define it as a power also. So power in this watt. So joule per second can be written as watt per meter per Kelvin. So this is the units of thermal conductivity in CGS system and also in SS system. So today we stop here. In the next class we will discuss the next topic. Thank you, students.